Yes, I welcome all of you once again for the session 2 of day 11 GATE training program on subject Municipal Solid Waste by Professor Roopapriya J K. Professor Roopapriya J K working as assistant professor and also she is serving as training and placement officer, having over 13 years of teaching and research experience. She obtained her bachelor degree from Vidyavarta College of Engineering in Environmental Engineering and master degree in Environmental Engineering from PS College of Engineering, Mandya. And also she offers consultancy services related to water quality. In today's session, she will be speaking on municipal solid waste pertaining to GATE 2021. With a short note, I request Professor Roopapriya J K to take over the session. Over to Professor Roopapriya, ma'am.
Thank you so much, sir, for that introduction. I would like to share my screen now. Dear GATE aspirants, I feel extremely delighted to discuss few topics related to municipal solid waste management in this GATE coaching. Let us spend some time together in understanding the concepts required to crack GATE 2021. So today is GATE 2021 coaching on environmental engineering, and my topic is municipal solid waste management, and this is session 2 on day 11. This is our topic for the day. And these are all the topics which are included in section 5 of environmental engineering in GATE 2021. We have water and wastewater quality and treatment, we have air pollution, and we also have municipal solid waste, under which we will be discussing characteristics, generation, collection and transportation of waste, and engineered system for solid waste management. So under municipal solid waste, as I mentioned, we have 4 important topics to discuss. One is about the characteristics of municipal solid waste. The second one is the generation of municipal solid waste. The third one is the collection and transportation of solid waste. And the last one is engineered systems for solid waste management. There are few papers which you can refer, and this is just 1 or 2 samples to tell you how many questions do come under this section, which is of municipal solid waste. So you can expect at least 9 questions to 10 questions. If you have 9 questions, you can expect 14 marks with 5 questions with 2 marks and 4 questions with 1 mark. If you get 10 questions, if you can expect 10 questions, then you have 16 marks with 6 questions of 2 marks and 4 questions with 1 mark. So this is just a sample for you to understand that these could be the number of questions and this could be the marks allotted for these number of questions. To understand solid waste management better, I would like to share with you a simple definition of waste and solid waste. Waste or wastes are unwanted or unstable materials. It can be considered as substances or objects which are disposed of or intended to be disposed of or are required to be disposed of. When we talk about solid waste, it means any garbage or refuge, sludge from wastewater treatment plant, water supply treatment plant, or air pollution control facility, and any other materials that is discarded resulting from industrial, commercial, mining, agricultural operations, and even from community activities. So this is solid waste. So let's move on to the types of solid waste. To understand the different types of solid waste, we shall have this simple flowchart. So solid waste are categorized into hazardous and non-hazardous wastes. And under hazardous waste, we do have municipal solid waste, agricultural waste, industrial waste, which includes construction and demolition, medical waste, special waste, and treatment plant waste. Under hazardous waste, we do have household waste. And again, we have different industrial waste, which are listed universal, characteristic, and mixed type of waste. So this is the different types of solid waste. This is about solid waste management. If these are the waste which we are generating, then how do we manage it? So this is a simple process again about the municipal solid waste management. So right from the generation to collection of the waste, the transportation of the waste, transporting the waste to processing units, and also the ultimate disposal is the actual management process. So, this is a simple example of municipal solid waste management in the recent days. The waste which is generated at source is collected, it is segregated at source, and it is transported to the disposal site. This is another simple example to identify the generation of the waste at source and how the waste is being segregated at source. It is segregated as biodegradable waste, recyclable waste, and residual wastes. And it is then collected and transported, which is either transported to processing units or it is also transported to the landfilling, which is the ultimate disposal. The characteristics of solid waste. It is very important for us to understand the various characteristics of solid waste. There are three different characteristics of solid waste. We can also call it as the three different properties of solid waste. The first one is the physical characteristics or the physical property of any solid waste, which includes the specific weight of the solid waste, the moisture content of the solid waste, particle size and size distribution, field capacity, permeability of compacted waste. So, all these are the physical parameters of solid waste. The chemical parameters of solid waste are the proximate analysis, fusing point of ash, ultimate analysis, and energy content. And the last, the biological property of solid waste is the biodegradability of organic waste components, production of odor, and lastly, the breeding of flies. So these are the three different characteristics of solid waste. I would like to first discuss the physical characteristics of solid waste. Under physical characteristics of solid waste, we do have the specific weight, or sometimes we call it as the density of solid waste. The specific weight is defined as the weight of a material per unit volume. It can be expressed either in kg per meter cube, or pound per feet cube, or pound per yard cube. Specific weight data are often needed to assess the total mass and volume of the waste that must be managed. It usually refers to uncompacted waste, and it varies with geographical location, season of the year, and length of time in storage. This is the typical specific weight values. These are the standards, and these are being used in most of the calculations. So it is very important for us as an engineer to remember the typical weight of these components. So these are the components which are the solid waste components. So I have taken few examples because these are the components mentioned in some of the question papers, and we will be solving few questions based on these components. So for food waste, paper, cardboard, plastic, garden trimming, wood, and tin can, there is a specific range and there is a typical value for specific weight. So we have to consider this typical value to calculate the specific weight of the solid waste. This is one of the questions which I have picked up from one of the question papers. This is related to the specific weight of the solid waste or the density of the solid waste, and it carries 2 marks. The question goes like this. Estimate the as discarded density of a solid waste sample with the composition given below. The composition given are the composition of various components, that is food waste, paper, cardboard, plastic, garden trimmings, wood, and tin can. The question also has the percentage by mass value, and the typical density in kg per meter cube is also given in the problem. How do we solve this? So here goes the step. The step 1 includes the calculation of volume, that is in meter cube. Volume is nothing but the percentage by mass divided by the typical density. That gives you the volume in meter cube. So you have to use the values given under the column percentage by weight, and also consider the typical density given in kg per meter cube. So when you divide the percentage by mass and the typical density, you get the volume in meter cube. So in this question, you have to calculate the volume for each and every component and compute the last table, which is volume, and then add all the volumes of the components. So according to this Question: the total volume is 1.107. Step 2. You have to calculate the density or specific weight using the equation total weight divided by total volume. So, which is 100 divided by 1.107. 100 is the weight, the percentage by mass taken into consideration, which equates to 100 kg. So, we are considering that 100 by weight to the total volume which you have calculated or computed in the last column, that is 1.107, and that gives you 90.33 kg per meter cube. So this is the solution to your problem. There's another question. This is again picked up from another question paper, a similar question where you have to again find the specific weight of the various components. So this is a question which carries again 2 marks. It's a very simple question and it has only 4 different components, so it should be easy for you to solve. So the question goes like this: the composition of a certain municipal solid waste sample and specific weights of its various components are given below. And the question continues: the specific weight in kg per meter cube of the municipal solid waste sample is, they have given 4 different values and you have to calculate and find out which is the right answer. So the question has the component, the percentage by weight, and the typical density given in kg per meter cube. So you have the 3 columns. And as you know, our step 1 is to calculate the volume using the percentage by mass divided by typical density, and you get volume in meter cube. So when you add the percentage by mass, you get the numerator value, the total weight, and when you add the volume, you get the denominator value, that is 0.456. So our second step is to find the density or the specific weight, which is equal to total weight divided by total volume. So now we know that the total weight is 100 divided by 0.46, which gives you 217 kg per meter cube. So that is the solution to your problem. So these are the 2 questions. This is simple. You just have to follow these 2 simple steps and then you get your answer and you get your 2 marks. So this is about density or the specific weight of municipal solid waste. Next, it is about the moisture content. Moisture content is again very important for us to understand. So moisture content of solid waste is usually expressed in 1 or 2 ways. In the wet weight method of measurement, the moisture in a sample is expressed as a percentage of the wet weight of the material. And in the dry weight method, it is expressed as the percentage of the dry weight of the material. The wet weight method is used most commonly in the field of solid waste management. We also have an equation for moisture content. So the equation for the wet weight moisture content is expressed as M is equal to W minus D divided by W into 100, where M stands for moisture content in percentage. W stands for initial weight of sample as delivered in kg. D is the weight of sample after drying at 105 degrees centigrade. And the typical range of moisture content is 15 to 40%, and it completely depends on the composition of the waste, season of the year, humidity, and weather conditions, particularly rain. This is the typical moisture content values. So just like how we had the previous slide where we had the density, we also have the moisture content value. I've picked up the same components because these are the same components usually asked in most of the question papers. So it is very important for you to remember these values. So we have the components: food waste, paper, cardboard, plastics, garden trimming, wood, tin can. And the range is given in column 2. Food waste has a range between 50 to 80. Paper has a range between 4 to 10. Cardboard has a range between 4 to 8. Plastic 1 to 4. Garden trimming 30 to 80. Wood 15 to 40. Tin cans 2 to 4. And the typical weight or the typical moisture content, that is percentage by weight, which we have to use in all our problems, is given in column 3. This is one of the problems. I wanted you to understand this problem because when we solve the problems later, we would require the calculation of moisture content also. So, this is one question based on a moisture content calculation. So, the question goes like this: estimate the moisture of a solid waste sample with the following composition. So the composition given is the food waste, paper, cardboard, plastic, garden trimming, wood, and tin can. And the percentage by mass is also given. So our step one should be setting up a computation table with the typical values of moisture content. So usually in the question papers, the moisture content is given. If they do not give it, then you'll have to remember the moisture content value and write the last third column, the moisture content with percentage. But usually they give the moisture content value, so you need not worry about it. So now you have three columns. The first column is about the component, the second column is about the percentage by mass, and the third column is about the moisture content in percentage. Now, how do we actually calculate the moisture content? Step two is to determine the dry mass of the solid waste sample using the percentage by mass and the moisture content data. So in our table, we do have percentage by mass value and also the moisture content data. For example, I've just picked up one component as an example to make you understand how you have to calculate the dry mass, which will be your last column, that is your fourth column. So if the component is given and the percentage by mass is given and also the moisture content is given, this is how you calculate the dry mass. You have to pick up the percentage by mass value and divided it by 100 and into 100 because it is in percent by mass, and that percent by mass is now in kg. So you get 15 into 100 divided by 100, which is equal to 15 kg. And this percentage by mass has to be again used along with the moisture content to get you the last column, that is the dry mass. So to calculate the dry mass again, you have to use the percentage by mass value, that is for food waste, it is 15. The moisture content in percent, now the moisture content in percentage is 70 percentage. So I've taken 70 divided by 100 to convert this into percentage. And we also have the percentage by mass, that is mass in kg, which is calculated as 15 kg. So 15 is the percentage by mass, which I've taken from the column 2. 70 by 100 is our moisture content in percentage, and 15 kg is the calculated value, which is in 15 kg in the first step. So this is how you calculate the dry mass and you get your last column ready. So to evaluate the moisture content, you have to compute the last column, which is the dry mass in kg. So after you calculate the last column, which is the dry mass, you have to add all the dry masses of all the components. And according to this particular question, the percentage by mass value, the total percentage by mass value is 100, and the total dry mass in kg is 79. Step 4. Determine the moisture content using the equation and the data from the table. So we have the equation moisture content M is equal to W minus D divided by W into 100. Now the dry mass D is 79. So our moisture content will be equal to 100 minus 79 divided by 100 into 100, which is equal to 21%. So 21% of the moisture content is present in this total solid waste component. This is another question, which is again related to moisture content, a simple question with the same parameters or the components. So we have the question like this: estimate the moisture content of a solid waste sample with the following composition. So we have the same components, but the percent by mass varies because it's in the range, so you can have different values. So step one, as we know, we have to compute the third column, that is the moisture content. If given, you have to consider the same column. If it's not given, you have to extract it from the typical value. So it is mostly given, so you'll have three columns and you have the moisture content in the third column. So after we have this moisture content, again, the calculation for dry mass, we have to consider the same calculation and compute our last column, which is the dry mass in kg, and add all the dry masses and then find out the total dry mass present in this solid waste sample. According to this question, the total dry mass in kg is 60 kgs. Now use the 60 kg in the equation to calculate the moisture content. So we know that the equation to calculate the moisture content is W minus D divided by W into 100. Here D is our 60 kg. So here goes the value 60, and then the moisture content is calculated as 100 minus 60 divided by 100 into 100, which gives you 40% of the moisture content present in this composition of the component in the municipal solid waste. So this is about moisture content. Next physical parameter is the particle size and particle distribution. The size and size distribution of the component materials in solid waste are an important consideration for the recovery of the material. Measurement of size distribution of particles in waste stream is important because of its significance in the design of mechanical separators and shredders. So all these are required when we plan the processing unit. So when we plan to recover the materials, we need certain equipments like the mechanical separators and the shredders. So that is why it is very important for us to identify the size and also find the size distribution of the component material which is present in the solid waste. So this is another very important physical parameter of the solid waste. Next, the field capacity, which is again the physical parameter. The field capacity of solid waste is the total amount of moisture that can be retained in a waste sample subject to the downward pull of gravity. The field capacity of waste material is of critical importance in determining the formation of leachates in landfills. Water in excess of the field capacity will be released as leachates. We will be discussing about leachates and landfills in the end. Moving on, the second property of solid waste is the chemical property. Under chemical property, we have different categories again. So it is very important to understand the chemical property and the information on the chemical composition of the components that constitute the municipal solid waste is very important in evaluating alternative processing and recovery options. So it is very important for us to understand the chemical composition to also identify the various alternative processing and recovery options. For example, the feasibility of combustion depends on the chemical composition of the solid waste. If solid waste are to be used as fuel, the four most important properties to be known are: one is the proximate analysis, the second one is fusing point of ash, the third one is ultimate analysis, and the last one is energy content. For us, energy content is an important parameter. We will solve few questions on this energy content as well. Proximate analysis. Proximity analysis is important in evaluating the combustion properties of waste or a waste or refuse or the refuse waste derived from fuel. Proximity analysis for the combustible components of municipal solid waste includes the following different tests. One is the moisture content, that is the loss of moisture when heated to 105 degrees centigrade for 1 hour. Next is the volatile combustible matter. This is the additional loss of weight on ignition at 950 degrees centigrade in a covered crucible. The third one is fixed carbon, that is the combustible residue left after volatile matter is removed. Last one is ash, the weight of residue after combustion in an open crucible. This is the proximate analysis. The fusing point of ash. The fusing point of ash is defined as that temperature at which the ash resulting from the burning of the waste will form a solid which is called as clinker by fusion and agglomeration. Typical fusing temperatures for the formation of clinker from solid waste range from 2000 to 2200 degree Fahrenheit, that is 1100 to 1200 degree centigrade. Next, ultimate analysis. Ultimate analysis refers to an analysis of waste to determine the proportion of carbon, hydrogen, oxygen, nitrogen, and sulfur, and the analysis is done to make mass balance calculation for a chemical or thermal process. Besides, it is necessary to determine ash fraction because of its potentially harmful environmental effects brought about by the presence of toxic metals such as cadmium, chromium, mercury, nickel, lead, tin, and zinc. So these are the typical energy content values. So as I mentioned, we will be solving one or two questions under this energy content. So it is very important for us to remember the typical values, or sometimes in most of the questions, they've already given the typical values. So you just have to know that these are the components and this is the range and this is the typical energy content, which is expressed either in BTU per pound or kilojoule per kg. There are a few questions which I'll be solving under energy content. So this is one of the questions picked up from one of the question papers. So the question goes like this. Estimate the energy content of a solid waste sample with the following composition. The question continues, what is the content on a dry basis and on an ash-free basis? So it is about what is the energy content on a dry basis and on ash-free basis. So the question is about the component of the solid waste. It also has the percentage by mass values. It also has the moisture content given in percentage, and they've also given the energy in kilojoule per kg. And this question may carry 2 marks. In most of the question papers, this question is for 2 marks. So this is the solution. This is how you have to calculate. It's very simple. The step one is about computation of the table, which is again of the dry mass. So here you can see the dry mass is calculated as we did previously when we were calculating the moisture content. So use the same calculation, use the same equation and find out the dry mass and compute the third column, which is the dry mass in kg. So we have the percentage by mass. We had moisture content in percentage. Now calculate dry mass in kg from percentage by mass and moisture content data. Step two, you have to compute the total energy in kilojoule. That is the total as discarded energy in kilojoule of the solid waste sample using the given data. So here in the table, we have calculated the dry mass in kg. Now you have to calculate the total energy in kilojoule. And it is a very simple calculation. You can calculate this total energy by multiplying the percentage by mass, that is your second column, into the energy in kilojoule per gauge kg. That is again given in your question. So according to this slide, you can see the second column and the fifth column, that is the energy in kilojoule per kg, is actually multiplied. So I've given you an example. Example for food waste, the total energy for the food waste is 15 into 4,650, which is the energy given in kilojoule per kg. That amounts to 69,750 kilojoule. So this total energy has to be calculated for each and every component given in the question. That is for food waste, paper, cardboard, plastic, garden trimming, wood, and tin can. And add all these total energy values. Also add the dry mass value, which is in kg. So according to this question, the total of the dry mass and the total of energy is calculated. This is your step three. Here you have to calculate the moisture content and the energy content. As you know, moisture content calculation is very simple. So you've got 79 as the moisture content in the previous, that is the dry mass in kg. So you have to use that value here. So moisture content will be equal to 100 minus 79 divided by 100 into 100. That is 21%. And unit energy content is calculated by the total energy in kilojoule, which is obtained by this computational table, and that divided by 100 kg of the waste. So that gives you 14,740 kilojoule per kg of the unit energy content. Now the question is about dry basis, that is the energy content on a dry basis. So to calculate the energy content on a dry basis, you need both the moisture content of the waste and the energy, the unit energy in kilojoule per kg. So you can compute the energy content in dry basis using this equation. If you have to calculate the energy content on an ash-free basis, you have to assume the ash content, which can be equal to 5%. This is an assumption. You can assume the ash content as 5%. And the energy content on an ash-free basis is computed as given in this equation. So energy content in kilojoule per kg, which is the ash-free dry basis, will be equal to the total energy in kilojoule per kg. That is, it was computed as 14,740 into 100 divided by 100 minus the ash content which you have considered, that is the 5%, minus the moisture content, which is your 21%. This gives you the energy content which is ash free on a dry basis, which is again in kilojoule per kg. So most of the times they ask you to solve only for the energy content on dry basis, and very rarely they ask you to calculate the energy content on an ash free basis. So if you're able to compute up to this step 3, then you're done with the problem. Let me take another example. So this is again a question which is asked in one of the question papers. The question goes like this. The composition of a municipal solid waste sample is given below, and they're asking the difference between the energy content of the waste sample calculated on a dry basis and as discarded basis in kilojoule per kg. So this is the question, and the table given is the similar table which has the same component, and the second column has the percentage by mass value, the third column has the moisture content in percentage value, and the last column has the energy content in kilojoule per kg on as discarded basis. So this is the question. Now let's see how do we have to solve it. So as you know, we'll have to first calculate the dry mass. So the step 1 would always be to set up a computation table to determine the dry mass in kg from percentage by mass and the moisture content data. So you get the column which is of the dry mass in kg. Add this column values, you get 79 kgs. Next, you have the energy in kilojoule per kg. Next step is to calculate the total as discarded energy in kilojoule of the solid waste sample using the data given in the table. So we have computed the dry mass, we have the energy. Now we can easily calculate the total energy by taking the values of the components, the percentage by mass value components, and the energy. That is column 2 into the column 5. That is, if, for example, if we're taking food waste, it is 20 into 2,500, which is equal to 50,000. If it is for paper, it is 10 into 10,000, it is 1 lakh. So this is how you compute the total energy column. And then you add all these values. So according to this question, the total energy of this specific solid waste sample is 5,80,500 kilojoule. And the dry mass, total dry mass is 60 kgs. So our last step is to calculate the moisture content and the energy content. We have the dry mass in kg as 60. So our moisture content will be equal to 100 minus 60 divided by 100 into 100, which is 40%. We have to also calculate the unit energy content, which is the total energy divided by 100 kg of the solid waste. So that gives you the energy content in kilojoule per kg. The last step is to calculate the energy content on a dry basis. So we have the moisture content as 40%. The energy on a dry basis is calculated using this equation. So the energy in kilojoule per kg on a dry basis is equal to the unit energy content, which you have calculated as 5,805. That into 100 divided by 100 minus the moisture content, which is 40%. So that gives you 9,675 kilojoule per kg. But the question is about the difference between the energy content of the waste sample calculated on a dry basis and as discarded basis. So now we have 9,675 kilojoule on a dry basis, and on discarded basis, we have 5,805 kilojoule per kg. So when we find the difference between these two, we get 3,870 kilojoule per kg, and this is the answer for this particular question. So the answer is the difference between the energy content of the waste sample calculated on dry basis and as discarded basis is equal to 3,870 kilojoule per kg. If you're asked to calculate the energy content on an ash-free basis, as mentioned earlier, you just have to assume the ash content as 5%. Use the simple equation where you're taking the energy content, that is the unit energy content of 5,805 kilojoule per kg into 100 divided by 100 minus the percentage of the ash content, that is 5%, minus kilojoule per kg. And when you have to take the difference, use this 10,555 minus the unit energy content, which is your 5,805, and that gives you the difference between the energy content of the ash-free dry basis and as discarded basis. So if asked, you just have to use this one liner which says assume the ash content equal to 5%, and then you get your energy in kilojoule per kg for ash free dry basis. So these are the two problems which I wanted to share. So that's about energy content. So that's about the properties of solid waste. Now moving on to the next topic, that is generation of solid waste. The information on waste quantity and composition is important in evaluating different alternatives in terms of equipment, systems, plans, and management programs. For example, if waste generated at a commercial facility consists of only paper products, then the appropriate equipment required is the shredder and the balers. So that is why it is very important for us to understand the type of the composition or the quantity of the solid waste and the composition of the solid waste. Similarly, on the basis of the quantity generated, we can also plan appropriate means for separation, collection, and recycling programs. That is to say, the success of any solid waste management depends on the appropriate assessment of the quantity of the waste generated. So, if we have to manage the solid waste very well, then it is very important for us to understand or assess the quantity of the waste generated. The waste generation encompasses those activities in which the waste, be it be solid or semi solid material, no longer has sufficient economic value for its processor to retain it. The processing of raw materials in the first stage when wastes are generated, and the waste generation continues thereafter at every step in the process as raw materials are converted into final products for consumption. So this is the material flow of waste. There's a simple flow chart which has the raw materials, the different manufacturing, the residues coming out of the raw materials, the residues coming out of the manufacturing process. It goes into the secondary manufacturing, and you also have the processing and recovery from the secondary manufacturing. We have the consumer, final disposal, and the waste material. So this is a simple flow chart which has the relationship between the raw materials, manufacturing, consumer, processing and recovery, and the final disposal. So this figure suggests that we can reduce the amount of solid waste by limiting the consumption of the raw materials and also by increasing the rate of recovery and reuse. The changes in waste generation contributes to the changes in waste composition. So if the changes in the waste generation contributes to changes in the waste composition, so what is this waste composition? The waste composition varies with the socio-economic status within a particular community. Since income, for example, it determines the various lifestyles, composition pattern, and even cultural behavior. Waste composition also depends on the moisture content, the density, and relative distribution of municipal solid waste, and is important for the characterization of solid waste for most applications. The density of waste changes as it moves from the source of generation to the point of ultimate disposal, and such factors as storage methods, salvaging activities, exposure to weather, handling methods, and decomposition influence the density. In short, predicting changes of waste composition is a difficult task as forecasting the waste quantities. These are the factors that affect the waste generation rate. So there are various factors. The first one could be the source reduction and recycling activities. This is one of the factors which affects the generation rate. The generation of the waste can be reduced at source. We can also involve recycling activities. So that is one of the factor. It also depends on the public attitude and the various rules and regulations and the legislations formed by the regulatory authority. It also depends on the geographical location and the physical factors. This is another factor that affects the waste generation rate. It also depends on the season of the year, the collection frequency, and also the population diversity. So these are the factors that affect waste generation rate. Collection of solid waste. How are we collecting the solid waste generated at source? So, the collection of solid waste refers to gathering or picking up of the waste, that is the solid waste, from various sources, and also the hauling of the waste to the location where the contents of the collection vehicles are emptied. So, collection has both the gathering and picking up of the solid waste, and it also refers to the hauling of the waste to the location where the contents of the collection vehicles are emptied. Unloading of the collection vehicle is also considered as a part of collection operation. These are different collection of waste procedures which are followed from a low-rise detached dwellings. The different ways are there is a curb collection, there is alley collection, there's a set out setback collection, and there is also set out collection. If it is a low and medium rise apartment, we follow the curbside collection process. If it is a high rise apartment, we use large containers for collection of the waste. So these are different types of collection of the waste from different types of dwellings. The different types of collection systems include two types of container system. So this is the collection systems which is classified according to their mode of operation. So depending on the mode of operation, we do have two types of systems. One is the hauled container system. The second one is stationary container system. The different types of hauled container systems are one is the hoist truck, the second one is the tilt frame container, the third one is the thrash trailer. The types of stationary container systems include systems with mechanically loaded collection vehicle and the system with manually loaded collection vehicle. Transportation of solid waste. So we have covered the generation of the solid waste, we have covered the collection of the solid waste, and now we have to transport the solid waste. That is why this topic is also important. Transfer stations. Transfer stations are used to accomplish transfer of solid waste from collection and other to small vehicles to larger transport equipment. Depending on the method used to load the transport vehicles, transfer stations may be classified into three types. The first one is direct load, the second one is storage load, and the third one is combined direct load and discharge load. Next, it is about the engineered systems for solid waste management. Once municipal solid waste is generated, it must be managed somehow. The usual management alternatives are recovery for recycling and composting. We also have reduce, reuse. These are also the other alternatives. We also have combustion procedures, and we also have the landfilling method, which is one of the solid waste management procedures. So these are the engineered systems used for solid waste management. Energy recovery. Energy recovery is derived from municipal solid waste in two forms. One is directly by burning as a fuel to produce steam, and indirectly through the conversion of waste to fuel, that is, the oil gas, or fuel pellets that can be stored for subsequent use. Once solid waste has been converted to thermal energy in the form of steam by combustion, or to chemical energy in the form of gases or liquids by pyrolysis or gasification, it can be converted to mechanical or electrical energy. Steam can be directly used for industrial purposes or building heating. Steam can be used to produce mechanical or electrical energy with a steam turbine. The gases and liquids produced from solid waste by both thermal and biological processes can be used to the fuel boilers to produce steam, and it can also be directly used to fuel reciprocating engines. The last is the disposal of municipal solid waste. So the municipal solid waste is ultimately disposed. So starting from the generation to collection, transportation, we do have certain processing units where we have the reuse, recycling, recovery methods, and then ultimate disposal is either on the landfills or we either combust it. That is the combustion process. So let's see what are these landfills. Landfills are the most economical and environmentally acceptable methods for disposal of solid waste. The landfill management incorporates the planning, design, operation, closure, and post closure control of landfills. Landfill can be defined as the physical facilities used for the disposal of residue solid waste in the surface soils of the earth. There are different methods of landfilling. So these are three different methods of landfilling. One is the excavated cell, or we also call it as trench method. The second one is the area method. And the last one is cannon or the depression method. Disposal, that is the landfills as a disposal site. So, as mentioned earlier, the landfilling methods include the excavated cell method or the trench method. It can also have the area method. It can also have the canyon or the depression method. And very important factor or two important factors which we have to consider during the landfilling is the landfill gases which is produced and the leachates which percolates below the ground. There are a few problems on landfills, which is given in some of the question papers. So let us now take up few problems on landfills. The question goes like this, and it carries 2 marks. The question is, a city generates 40 into 10 to the power of 6 kg of municipal solid waste per year, out of which only 10% is recovered or recycled, and the rest goes into the landfill. The landfill has a single lift of 3-meter height and is compacted to a density of 550 kg per meter cube. If 80% of the landfill is assumed to be municipal solid waste, the landfill area in meter square up to 1 decimal place required would be dash. So first of all, we have to analyze the data given in this problem. It speaks about the quantity of the waste generated in kg. It also speaks about how much of percentage of this waste is actually recovered or recycled and how much of it is going into the landfill. So if you're having the 10% recovered, then the 90% of it should go single lift of 3-meter height, and it is a compacted waste to a density of 550 kg per meter cube. So this is the compacted waste. And now the question also says if 80% of the landfill is assumed to be the municipal solid waste, the landfill area which is required should be equal to these many meter square. So let's see how do we solve this simple problem on landfills. This problem carries 2 marks. So these are the different steps, and this is the solution for this particular problem. So according to the problem, the data given, that is the total waste generated for the year, is 40 into 10 to the power of 6 kg. And the municipal solid waste that goes into the landfill is the 90% of this waste which is generated per year. So according to this value, now because we are taking only 10% as the recovered or the recycled, so 90% is used for the landfilling purposes, we have 36 into 10 to the power of 6 kg according to this calculation. We also have the compacted density of the waste given in the problem. So according to the problem here, it says the landfill has a single lift of 3-meter height and is compacted to a density of 550 kg per meter cube. So let's use this value and find out the volume of the waste. So considering the municipal solid waste that goes into the landfill divided by the compacted density of the waste, that is equal to 550 kg per meter cube, we get 65,454.54 meter cube as the total volume of the waste. So this is the total volume of the waste, which is calculated using our value, that is the total amount of the waste, of generated waste which goes into the landfill, divided by the compacted density of the waste. Now, because we have to calculate the area in meters cube, meter square, which is the area of the landfill, the simple calculation here is we have in the question 80% of the landfill is assumed to be municipal solid waste. And now we have to find out what should be the area of the landfill in meter square. So that is why the municipal solid waste land area will be equal to 80% of the area. Now that is calculated by considering the total volume of the waste and the 3-meter lift, which is mentioned in the problem. So we're considering 80% of the landfill, which is assumed as the municipal solid waste area, and the landfill has a single lift of 3 meter. So the area, according to this calculation, will be 27,272.7 meters square. So that is the solution to the first problem. So you can always fill this question as, the question goes like this: the city generates 40 into 10 to the power of 6 kg of municipal solid waste per year, out of which only 10% is recovered or recycled, and the rest goes into the landfill. The landfill has a single lift of 3-meter height and is compacted to a density of 550 kg per meter cube. If 80% of the landfill is assumed to be municipal solid waste, then the landfill area required would be 27,272.7 meters square. So this will be the answer for your question. The second problem on landfills, it's a similar problem, so I will read it slowly. A landfill is to be designed to serve a population of 2 lakhs for a period of 25 years. The solid waste generation is 2 kg per person per day. The density of the uncompacted solid waste is 100 kg per meter cube, and a compaction ratio of 4 is to be suggested. The ratio of the compacted solid waste is 1.5. The landfill volume in million meter cube required is dash. So this is one of the problems asked in one of the question papers, and it carries 2 marks. So let's see how do we have to solve this question. Again, simple steps. The solid waste generated per day will be equal to the population into the kg generated, that is the generation of the solid waste, which is given as 2 kg per person per day. So we have this 2 kg per person per day. We have 2 lakh people. So the solid waste generated per day will be 2 into 2 lakhs, that is 4 lakh kg of the waste generated per day. Total solid waste generated in 25 years will be, considering 365 days, we have 4 lakh into 365 days, which gives us the actual volume or the total solid waste generated in 25 years. So the compaction ratio given is 4 according to the problem. So the compaction ratio is calculated by volume before compaction divided by volume after compaction. Now, to calculate volume of waste before compaction, we can use the value which is computed here. It is 3.65 into 10 to the power of 9 divided by 100, which gives you 3.65 into 10 to the power of 7 meter cube. So this will be the volume of waste before compaction. Now we have the numerator value, that is volume before compaction. Now we have to compute the volume after compaction. So here it says, in the problem, it says the density of the uncompacted solid waste is 100 kg per meter cube, and the compaction ratio of 4 is suggested. So that's why we have considered this 4 here. So volume of the waste after compaction will be equal to this 3.65 into 10 to the power of 7 divided by 4, which will be equal to 9.125 into 10 to the power of 6 meter cube. So our solution would be, because we also have the solid waste and the cover in the landfills. So solid waste plus the cover divided by solid waste, we have 1.5 in the problem. So this is the ratio of the compacted solid waste, which is given as 1.5. Considering that, we have the cover divided by the solid waste as equal to 0.5. Now the cover will be equal to 4.5625 into 10 to the power of 6 meter cube as per the calculation. So now for the total volume, we need the solid waste plus the cover. So considering the total solid waste generated and the cover, we have 13.68 million meter cube of the total volume of solid waste. So this will be the solution for your problem on landfills. So this is the question, and this is the simple step. So the solid waste generated per day, that is in kg. Total solid waste generated in 25 years. Compaction ratio, which is calculated using the volume before compaction and volume after compaction. The solid waste cover, the landfill cover and the solid waste. And the total volume is equal to the solid waste plus the cover, and that gives you 13.6875 million meter cube, which is the total volume, and this is the solution to your landfill problem. The next problem is on greenhouse gas production. So there are a few questions which are based on this greenhouse gas production. So this is one of the questions, and this again carries 2 marks. So the question goes like this: 50 grams of carbon dioxide and 25 grams of methane are produced from the decomposition of municipal solid waste with a formula weight of 120 grams. What is the average per capita greenhouse gas production in a city of 1 million people with a municipal solid waste production rate of 500 ton per day? So these are the different questions. The options given are A, 104 gram per day. Option B, 120 gram per day. Option C, 208 gram per day. Option D, 313 gram per day. So first of all, we have to find out what is the data given and how do we compute this simple problem. It's a very easy problem. So first of all, let us try to understand the question. So it says, according to this problem, it says 50 grams of carbon dioxide and 25 grams of methane are produced from the decomposition of municipal solid waste with a weight of 120 grams. And the number of people, the population is 1 million, and the municipal solid waste production rate is 500 ton per day. So the data given, we have the municipal solid waste quantity as 120 grams. We have a population of 1 million. So we also have the gas production, that is 50 grams of carbon dioxide and 25 grams of methane, which is produced according to the problem. So with this given data, let's find out what could be the total greenhouse gas produced from both carbon dioxide and methane, which are the greenhouse gases. And these are usually produced in the landfills. So we have 50 grams plus 25 grams, which is equal to 75 grams from the 120 grams of municipal solid waste quantity, which is mentioned in the problem. So 75 grams of this greenhouse gases are produced from a municipal solid waste quantity of 120 grams. Also given, municipal solid waste production rate is 500 ton per day. So using this, we'll have to calculate the per capita greenhouse gas production. We have 75 grams from 120 grams of municipal solid waste, which we have to consider in the calculation. So 75 divided by 120 gives you 75 grams of 120 grams of solid waste. We have 500 ton per day. So that is why it is important for us to find out what is the amount of the greenhouse gas produced in gram per day. So this is the conversion, 500 into 1000 into 1000, that is 10 to the power of 3, divided by 10 to the power of 6. So that gives you the actual value in gram per day. So this is a very simple calculation. You have been given all the values. All that you have to do is add the given values of the greenhouse gases. So here, according to this problem, you have the carbon dioxide and the methane as the greenhouse gases. There is 50 grams of one of the greenhouse gases produced and 25 grams of the methane, which is the greenhouse gas produced. Just add these two, find out how much of grams of this greenhouse gas is produced from the quantity present, that is the municipal solid waste quantity present. And considering the production rate given in the problem, just calculate the per capita greenhouse gas produced in the landfill. Okay, so this is the solution. So for your question, you have the options 104, 208, 120, and 313 gram per day, because this 312.5 is close to 313. So your answer for the question is 313 gram per day of the greenhouse gas produced. Okay, so this is about the greenhouse gas. And to quickly take you through all the questions which we solved, a quick wrap up. We had the physical property, a quick wrap. One question on the density or the specific weight. You may be given the component, the percentage by mass, and typical density in kg per meter cube. Please remember, this will be the type of the question which will be asked in your question paper. So considering these values, step one would be to find out the volume. So let me repeat, you'll have to calculate the density using this. The last column, volume, is very, very important. So you have to calculate the volume using the percentage by mass value and the typical density value. So percentage by mass divided by typical density will give you the volume. Compute the last column, which is the volume in meter cube. Add all these volume values, you'll get the total volume. Calculate the density of the solid waste, which is equal to the total weight divided by total volume. So according to the problem, the total weight is 100 kg and the total volume was 1.107. And this was your answer. 100 divided by 1.107 is equal to 90.33 kg per meter cube. So this is the simplest calculation of the density. So it will fetch you 2 marks easily. So this is about one type of the problem. Next, we had the moisture content. Moisture content was calculated using the formula M is equal to W minus D divided by W into 100, where M was the moisture content in percentage, W is the initial waste of the sample as delivered in kg, D is the weight of sample after drying at 105 degrees centigrade. The type of the question you'll be getting is, to estimate the moisture content given the percentage by mass and the moisture content of these components in percentage. All that you have to do is calculate the dry mass, compute the last column, which is the dry mass in kg, using both the percentage by mass value and the moisture content in percentage value. Sum up all the percentage by mass value. According to this problem, there is 100, total of 100 percentage by mass value for this particular problem with these many components. And the dry mass value, the total of the dry mass value is 79 kg. Use these two values to compute your moisture content, which is equal to 100 minus 79 divided by 100 into 100, which gives you 21%. So simple calculation, please remember how to calculate the dry mass in kg. So this completes your moisture content calculation. So one was about the density. This is about the moisture content. Next, we also discussed the energy content. This is the chemical property. As I said, energy content is usually asked in all the question papers. So please concentrate on this. Here, calculation of the moisture content becomes important. This is the kind of problem you will be getting to calculate the energy content. And sometimes they may ask you also the difference in the energy content. So to estimate the energy content, you would be given the component, the different components, the percentage by mass of these components, the moisture content of these components, and also the energy content in kilojoule per kg. So this will be the question, and this is for 2 marks. So the solution would be you have to compute the dry mass just like how you did previously for calculating the moisture content. Use the percentage by mass value and the moisture content and calculate the dry mass in kg. Add all these dry mass in kg and find out what is the total dry mass present in the municipal solid waste of these. This is the component. This is the sample component. And using this energy column and the percentage by mass column, find out what could be the total energy in kilojoule. So you can multiply the percentage by mass value into the energy given in kilojoule per kg. That will give you the total energy in kilojoule. Add all these values, find out what is the total energy in kilojoule produced from these components present in this particular sample of solid waste. According to this problem, you have dry mass as 79 and you have the total energy content as 1 lakh 14 lakh 74,000. Find out the moisture content. The simple calculation again, the moisture content is equal to 100 minus 79, which is the total dry mass present in the sample of municipal solid waste, divided by 100 into 100. That gives you the moisture content. Calculate the unit energy content, which is equal to the total energy calculated by you. That is the last column value, the total of this last column, divided by 100 kg. That is the total mass of that particular solid waste sample. That gives you the unit energy content. Now, using this unit energy content, find out the energy content on a dry basis. So use the moisture content value, use the unit energy content, and find out what could be the energy on a dry basis. That is again in kilojoule per kg. If suppose you're asked to calculate the energy content on a ash-free basis, assume the ash content as 5% and then calculate the energy content in ash-free dry basis again in kilojoule per kg. Okay, so this is about energy content. So sometimes if they ask you the difference between the energy content of the waste sample calculated on the dry basis and as discarded basis, what you can do is you can consider the unit energy content value and the energy content which you have calculated on a dry basis. You can find the difference between the unit energy content and the dry basis energy content and give the actual value of the difference between the energy content of the waste sample calculated on dry basis and as discarded basis. So this is about energy content. So we have covered the density, we have covered the moisture content, we have covered the energy content. Next, we discussed the landfills. So one simple problem under landfills. So this is the problem under landfills. So here, the quantity of the waste generated has been given, and how much of it is going to the landfills and what percentage of it is going to the recovery recycle is also is been given. The uh, the single lift of 3 meter height is also provided, and the density of the compacted waste is provided. And it also mentions how much a percentage of the landfill is assumed to be the municipal solid waste, and we'll have to identify what is the area of the municipal solid waste landfill. So this is the computation. First of all, we are finding out the total waste generated for year, and we're also finding out how much of municipal solid waste goes into the landfill, considering what percentage of it is going into the processing unit, that is the recovery, recycle, reuse. Considering the compacted density of the waste, we are calculating the total volume of the waste generated. And considering the percentage of the area required for landfilling, we are calculating the municipal solid waste land area in meter square. So this is about landfills. This was for 2 marks. So in this particular problem, again, about landfills, here the population was given, the generation rate was given, and we have calculated the volume before compaction, volume after compaction, because compaction ratio was provided. And then considering the solid waste and the cover of the solid waste, we have calculated the total volume, which is equal to the solid waste plus the cover. So this gives you the total volume in million meter cube. So this is one problem under landfills. And the last was the greenhouse gas production. This was again for 2 marks. So this is the type of the question you'll be asked, where the greenhouse gases produced are given or represented in grams. So here, according to this problem, 50 grams of carbon dioxide and 25 grams of methane are produced from the decomposition of municipal solid waste. And this is the formula weight of 120 grams. Average per capita greenhouse gas production of a city is also being provided, and the population is provided, and the production rate is provided. A simple calculation wherein you're actually finding out the greenhouse gas production, which is the total of the different types of gases produced. And then considering the production rate, you'll be calculating the per capita greenhouse gas production in grams per day. So these are the different types of questions you can expect in your question paper, that is GATE 2021, under Municipal Solid Waste Management. So that's it. Thank you so much. And I wish you all the best for your exams. I'm sure you're all preparing well. And this is one section you have to concentrate, because here again you have at least 14 to 16 questions based on municipal solid waste management.
Thank you, Professor Roopapriya, madam. It was a very informative session. So now I request your participants to find the feedback link in the YouTube chat box and kindly provide your valuable feedback for this session. I'd also request all of you to join us on day 12 of our training program tomorrow on 9th December at 2 p.m. And tomorrow we have two sessions. First session on wastewater treatment by Professor Sharmila A, followed by session 2 on geomatics engineering by Professor Girish P at 3:45 p.m. using the same YouTube channel. Thank you. Thank you all.
Thank you, sir, for giving me this opportunity. And I again wish all the GATE aspirants all the best and do well for your, prepare well and do well in the exams. All the best. Thank you.
Thank you, ma'am.